Hello, today our lecture will be focused on the design aspects of compression member with respect to built up sections. In last few lectures we have focused on design aspects of single compression member as well as the strength calculation of single compression member and the built up compression member. Today we will finish first the remaining part of the last lecture, that means how to calculate strength of a built up sections. Then we will go the design aspects of built up sections. Built up section design means we have to design the section in such a way that all the members will be acting as a whole together. So, the members has to be tied properly so that the all members will be acting as a whole for carrying the compression load, as well as we have to see also that the compressive load are distributed properly to all the members as we want. Therefore, we have to design not only the main members properly, but also we have to focus on design on the other members like lacing or battening. What is lacing and what is battening I will come later. Basically, the objective of providing all this extra type of plate is to connect the members each other, to tie the members each other, so that all members act together. Suppose we have say two I sections, then if we see in the say we will see that this is a battening or lacing. Now, if we see in the elevation, we will see that it is acting something like this. That means, we will be having some sort of lacing like this. This is called lacing system. Lattice members we have to provide. We will come details later. In continuation with the last lecture, we have seen that this type of members can be made with the use of individual members to find a built up section, and the major objective of choosing the built up section is that the radius of gyration in both the directions perpendicular to each other should be more or less equal. That means, the radius of gyration in the weaker section we are going to increase, so that the strength of the member is going to increase. First, I will discuss this problem, how to calculate the maximum strength of a particular system, and then I will go to the design aspect. So, let us consider this example, that a built up column of 4 meter effective length has to be made using 2 ISLC 350 at 38.8 kg per meter. To obtain maximum strength, what should be the spacing between the two channels if they are placed back to back and face to face as shown in the figure. That means, the two orientation we will give, the two channels are placed back to back and two channels are placed face to face. If we make in this way, then what will be the strength and what should be the spacing we have to calculate. Say first case is the channels are placed back to back. So, this is one channel, another channel is this, means with same size, this is called spacing S, and as we know, this is basically we can say CXX or CYY, this is called CYY, that means the CG of the channel, right, and this is the center of the group section, this is back to back channels with back to back. case A, and another orientation is something like this. This is one channel, another channel is this, which are placed face to face. So, x axis and y axis will be this, and individual, this is y axis, individual y axis. This is basically we know CYY, that distance from face to the CG of the system. Okay. So, now we have to find out what is the strength of the system if the channels are placed back to back, and what is the strength of the same members if they are placed in face to face with some spacing. Now, here spacing means this one, clear distance between two channel, right. So, this spacing we have to find out. That means spacing we have to find out means for maximum, means for obtaining maximum strength, what should be the spacing with these two orientation, that we have to find out. So, what we will do first? First we will find out the sectional properties for ISLC 350 at rate of 38.8 kg per meter. We know the sectional properties of a section which is given in IS code is available in SP 6 1962, the structural handbook SP 6, right. So, from there the properties of the channel section we can find out, like the individual property of ISLC 350 has been given, like the moment of inertia about x axis is 9312.6 into 10 to the power 4 millimeter to the power 4, which is obtained from structural handbook SP 6. Similarly, IYY is 394.6 into 10 to the power 4 millimeter to the power 4. RXS, the radius of gyration, is given 137.2 millimeter, RYY is given 28.2 millimeter, CYY is 24.1 millimeter, BF, the width of the flange, BF means the, if the channel is this, then we can say this is BF. Width of the flange is 100 mm, TW is the thickness of wave, that is given 7.4 millimeter, which will be required, and area of the section is given 4947 millimeter square. Remember, these the properties of a single section has been given in the code which has been written here. Now, if we see IXX is much greater than IYY, or in other word also we can say that RXX is much greater than RYY. RXX is 137.2 and RYY is 28.2. So, as we know, the compressive strength of the member depends on the radius of gyration, because if radius of gyration becomes less, the L by R ratio, that means slenderness ratio, will increase. Slenderness ratio increasing means the allowable compressive stress of the member will decrease, as because of buckling effect. So, to make the section economic, to take the advantage of that, we can do what? That we will place the channel section in such a way that this RXX will become RYY, right, or IXX will become IYY, so that the resistance from both the direction will come same. In a single section, resistance in this about this direction is very high compared to this direction. That is why, though the member is very strong about this x axis, but weak about y axis. As a result, the member is weak, because we have to see the strength from the weaker section point of view, from the weakest point of view, right, because failure will happen first in the weakest section. So, if we can increase the radius of gyration by placing in a proper way, then what will happen? We can increase the strength of the built up section. Now, suppose what we can do, up to what we will increase, because we know IXX is fixed, whatever placing we are doing, whatever S is we are making, IXX means IX combined IX is fixed, that is the summation of these two individual Ix. So, what we have to do? We have to increase the IYY up to what we will increase? Up to Ix, because after that if we increase again failure will start from Ix point of view, about x axis the failure will start. That is why what we will do? We will try to make equal, that means Ix equal to Iy. Unnecessary if we increase the Ryy value, means Ry value, that means radius of gyration about y axis, then what will happen? Unnecessary if we increase also, but strength will not increase after reaching Rx value, means Ix, okay, because failure will start in about x direction and we cannot increase that one by the placing of two channel section apart from each other, right. So, that is why for optimum we can make Ix is equal to Iy, right. So, that is what we will make it. So, first let us consider case A. Case A means the channels placed back to back, that means two channels are placed back to back. So, what we will do? First we will consider the equivalent Ix for the built up section. Ix means the moment of inertia about x axis of the built up section. If this is x, then Ix means 2 into Ixx, because Ixx individual Ixx we have here, right. So, 2 into Ixx will be the moment of inertia about x axis of the built up sections, right. So, Ix we can find out 2 into Ixx is equal to 2 into 9312.6 into 10 to the 4, which will be equal to 18625.2 into 10 to the 4 millimeter to the 4. So, this will be the moment of inertia of the built up section about x axis. Similarly, I can find out the moment of inertia about y axis of the built up section. When I am talking about y axis means this is the y axis, right. So, this will be what? This will be, we have individual Iyy, right. This is yy axis of the individual. So, what we will do? Iyy into, means Iyy is there plus that ar square, right. So, 2 into Iyy plus a into r square. What is r value? R means this is Cyy, the distance from the face to the CG of the section, plus this is the S. So, this will be S by 2. So, a into r square, that means a into Cyy plus S by 2 whole square, and into 2 y we have made because of two sections, right. So, Iyy can be find out from this expression. Now, if we put the values of those, we will get Iy is equal to 2 into 394.6 into 10 to the 4, which is Iyy value, plus area is individual area of the section is 4947 millimeter square, into this is the CG distance from the face 24.1 plus S by 2 whole square. And as we know, for optimum utilization of the two member, what we have to make? We have to make Ix equal to Iyy, that means we will place the sections in such a way that equal resistance will come from both the direction, right. So, if we make Ix equal to Iyy, what we will do? We will get, this is Ix, that is 18625.2 into 10 to the 4 is equal to 2 into 394.6 into 10 to the 4 plus 4947 into 24.1 plus S by 2 whole square. This is Iyy and this is Ixx, right. Now, if we make equal, then what we will get? That S by 2 plus 24.1 whole square will be equal to 9312.6 into 10 to the 4 minus 394.6 into 10 to the 4 by 4947. So, from this I can find out S by 2 plus 24.1 is equal to 134.26. That means S is equal to 220.33 millimeter. That means the spacing is equal to 220.33 millimeter. So, this is the spacing. If we can make, then we will get equal resistance from both the side. That means the Ix will be equal to Iy. So, I can find out the radius of gyration. That means the Ix value we know. Okay, now, radius of gyration we know. Radius of gyration is Ix by A or Iy by A. So, Ix means 2Ixx and A means area of the built up section, which is 2 into A, where small a is the area of the individual section. Now, after equating we will see Ixx by A. Now, if we put the value of Ixx and the area of the individual section, we will get R as 137.2 millimeter, right. And this is also directly we can find out from the SP6, right. So, lambda will become L by R. Now, the effective length has been given as 4 into 10 to the power 3 millimeter, means 4 meter, right, that means 4000 millimeter by R, radius of gyration. Radius of gyration is 137.2. This radiation gyration basically R means Rxx we can say, sorry, Rx we can say, or Ry also we can say, will be same. So, lambda, the slenderness ratio is becoming 29.15, right. So, now from this slenderness ratio value and for Fy equal to 250, if we assume the steel grade as 250, then from table 5.1 of IS 800, what we will get? We will get sigma AC, the permissible compressive stress in the member. That is, we will get from table 5.1, and this is coming sigma AC as 145.26 MPa, right. So, corresponding to lambda as 29.15 and Fy as 250, from table 5.1 of IS 800, we can find out sigma AC as 145.26 MPa. Thus, we can find out the strength of the built up section, which will be basically P is equal to sigma AC into A. Now, sigma AC we have calculated, that is 145.26 MPa, and area means 2 into cross sectional area of the individual section, that is 4947. So, 2 into 4947. Now, this is coming in Newton. If we divide by 1000, we will get kilonewton. So, finally, we will get 1437 kilonewton, right. So, this is the way we can find out the maximum strength, and this maximum strength we can find out if the spacing is becoming 220.33 millimeter. On these circumstances, we can find out the maximum strength as this, that means 1437 kilonewton. Now, let us come to the second case. Second case means channels placed face to face. That means, if one channel is like this and another channel is placed like this, then what should be the spacing to get the maximum strength of the member, right. So, like previous cases, we can find out Ix as 2Ixx and similarly Iy as 2Iy plus 2 into A into d square. What is d? D is the distance, which can be written as Bf minus Cyy plus S by 2. This is plus S by 2, right. How we are getting? That means, we have to find out here, right. So, this is S by 2. This we can find out S by 2, and this is Bf, and this is Cyy, right. So, what we will get? This distance we will get Bf minus Cyy, okay. So, the total distance from here to here we will get as d, which we have written, d will be Bf minus Cyy plus S by 2. Right. So, Bf minus Cyy plus S by 2. So, Bf is 100 mm, Cyy is 24.1 and S by 2 we do not know, as S is the spacing which I have to find out. So, this is becoming this d. So, Iy we can find out as Iy is equal to 2 into Iyy plus A into d square, where d is 75.9 plus s by 2, right. So, with the same concept that to get equal resistance from both the directions, if we make equal I x equal to I y, what will happen? We can find out the value of s. That means, if we make equal I x equal to this, so we can find out that 75.9 plus s by 2 whole square is equal to I x minus I y by a. That means, this minus this, I x is 9312.6 and I y is 394.6. So, by a is 4947 millimeter square, right. So, we can find out s by 2 as this one, and s can be find out as 116.73 millimeter. So, the spacing whatever we are getting from this expression is that s is equal to 116.73 millimeter. If we make spacing of this magnitude, then the equal resistance from both the directions will be obtaining, right. So, now the strength, how do we calculate strength? In the similar process we can find out where r is equal to I x by a, that means I x x by a, that means same thing. So, lambda will be similarly we can find out L by r, where the L is the effective length which is given as 4 meter or 4000 millimeter, and r we can find out that is 137.2. So, we can find out sigma AC value as 145.26 MPa from table 5.1 of IS 800 for FY grade of 250 MPa, right. So, in this way we can find out the strength of the built up section as same, that is 1437 kilonewton. See here, whatever combination we do, means whether back to back or front to means face to face, Ix will be same Ix, right, for both the cases, because Ix will be 2 into Ixx. Okay. So, the strength will be same, means maximum strength can be attained this much. Okay. Now, if we increase the spacing, the strength about IYY means strength about y direction will be increasing, but failure will start in x direction. Okay. But we cannot increase the strength about x direction, because that Ix will be fixed, that is 2 into Ixx. Okay. So, to get maximum strength, what we can do, that maximum radius of gyration Rxs we can attain by increasing the spacing, that S, by calibrating the magnitude of the spacing. Okay. Because spacing if we increase much more, then it will not work. What will happen? The strength about y direction will be increasing, but strength about x direction as we cannot increase. So, failure will be happening on this strength 1437 kilonewton, right. So, what we are getting, that the maximum strength of the built up section will be 1437 kilonewton for both the case. If spacing is kept 220.33 millimeter for case A and 116.73 millimeter for case B, right. So, which arrangement we should go? We should think, that is, however, the second arrangement is generally not preferred. Why? Because of fabrication, maintenance and inspection point of view. From these 3 point of view, the first case is preferable. So, generally we used to go first case, that is channel back to back. Okay. So, in this way generally we used to design if we have to consider 2 channels. We now understood that how to find out strength of a built up member. Now, we will go for the design process, that how to design a compression member having built up sections. This is exactly same as we have done for individual members, right. So, similar process we will follow for getting the design aspects of built up compression member. So, let us see how it happens. So, for design of built up compression member, we will see what are the steps we have to follow. In steps 1, what we do, that we can find out the effective length from the actual length and end conditions. That means, what will be the effective length LE, whether this is 0.65 L or 0.8 L or 1 L, means it depends on the boundary condition of the member, whether it is resistance against both the direction or resistance against its rotation. Okay. So, all these things we have to see accordingly, we have to find out the effective length. Then in step 2, what we can do, we can assume some value of lambda, radius of gyration, which will be between 30 to 60 for the built up sections. You see, lower value for I section and higher value for channel section. That means, if I section we can consider 30 and if channel section we can consider 60. So, in between 30 to 60 we can consider. One may ask, why 30 to 60, why not more? Because in case of built up section, we are taking the advantage of getting efficiency from both the section, both the side. That means, the RXX will become RYY. So, maximum radius of gyration we are going to attain. That is why the compressive strength, allowable compressive strength will be more, right. So, from the experience it is seen that if we consider built up section, the radius of gyration varies from 30 to 60 in between, near about. It is not exactly 30 to 60, it may be 70 or it may be 20 also, it depends on the type of arrangement whatever we are going to do, right. So, we have to first assume say lambda value, okay, say from 30 to 60 something we have to assume on the basis of our experience, or with this also for I section we can go for lower value and for channel section we can go for higher value, right. Then what we will do? Then we can find out the allowable compressive stress for the given value of lambda, right. For the assumed value of lambda, we can find out the allowable compressive stress, that is sigma AC, right, from table 5.1, where from lambda and Fy we can find out the sigma AC value. After that what we will do? We can find out the area required, that is the load by allowable compressive stress, P by sigma AC. The required area can be find out in this way. Then what we will do? We will come to step 5, that means we know the required area. So, accordingly we can choose a built up section so that the total area becomes more than the required area calculated in step 4. Okay. That means, the chosen area should be more than the calculated area which has been calculated in step 4. Then also arrange the members in such that the values of Ixx will become close to Iyy. This is important. We have to arrange in such a way, suppose we have 2I section. So, the distance between two sections will be in such a way that Ixx will become close to Iyy. So, Ixx means Ix will become close to Iy of the built up section, that we have to make. Okay. Then what we will do? With the above arrangement, find R minimum. R minimum is the radius of gyration, minimum radius of gyration. Now, to get maximum efficiency means get maximum strength of the member, we will get Rxx equal to Ry, Rx equal to Ry. However, if it is not possible, then we have to find out what is the R minimum, okay, and then calculate lambda max. R minimum means lambda max we will get, okay. Then again from table 5.1 you can find out the value of sigma AC. Sigma AC means the compressive stress, right. Now, calculate the developed compressive stress in the built up section. How we will develop? That sigma AC calculated will be P by A. A means A provided, right. So, whatever area we are providing from the built up sections, we can find out sigma AC calculated, and before that we have already calculated the permissible stress from the actual slenderness ratio and Fy with the help of table 5.1, right. So, now we will check if sigma AC calculated is less than sigma AC, then okay. Otherwise what will do? Otherwise choose a higher section and repeat the steps 5 to 7. That means again we will choose a higher section, then we will go to steps 5, then 6, then again, right. So, this will repeat till we are satisfied with this checking. That means, sigma AC calculated will be less than or equal to the permissible stress. Okay. So, this is the way what we have to do. So, what are the difference we are getting from the design aspects of single section and from the built up section? That is that we have to arrange the built up section, we have to arrange the 2 or more individual sections in such a way that we will be getting approximately equal radius of gyration in both the direction to get maximum benefit from that orientation, right. So, on that way we have to find out what will be the distribution of the members, means what will be the arrangement of the members, and then what will be the spacing of the member we have to find out, and in that way we can find out the sectional properties of the built up section as well as its spacing. Now, this is not the end of the design, because when we are say 2 channel sections we are providing. Now, when we are providing 2 individual channel section, it has to be tied up in such a way that it is acting as a whole. The section is acting as a whole, as a group. So, by the use of lacing or battening members. So, that will come later, but before that let us go through one example through which we will be seeing that how to design with these steps. So, let us go through this example, that is a double angle discontinuous struts has to carry a compressive load of 120 kilonewton. The length of the strut is 2.5 meter between intersections. The angles are unequal and placed back to back with longer leg connected and are tack riveted, right. Design the section if first case is, so case A, angles are placed on same side of 16 mm gusset plate, right. This is one, and second case is angles are placed on opposite sides of 16 mm gusset plate, right. That means, in first case, say this is the gusset plate. Now, it is told that longer legs connected. So, this is one, another one is this, right. So, this is case A, right. This is the gusset plate and the orientation will be like this for case A, and for case B, if this is the gusset plate, then remember that longer legs are connected with the gusset plate. So, this will be the longer, right. Now, these are 16 mm thick. These gusset plates are 16 mm thick. Okay. So, this is case B. So, what we have seen here, that the two unequal angles are connected with the use of gusset plate in two way. One is in the same side, another is in the opposite sides. Then we have to design the angle section with these two arrangement, and we have to see which one is better. We can see in fact that which one will be preferable, right. So, what we will do? See, if we go for solution. So, first what we will do? We will assume either some radius of gyration, or simply we can assume also sigma AC value. So, let me assume 70 MPa, right. So, if we assume say compressive stress, allowable compressive stress as 70 MPa, then we can find out cross sectional area required, right. That we can find out P was 120 kilonewton by sigma AC. This is P by sigma AC we are making. So, from this we can find out 1714 millimeter square. Now, as unequal angle has to be chosen, so from the IS handbook we can find out that 2 ISA 90 by 60 by 8, right. So, let us try with 2 ISA 90 by 60 by 8. Now, from this section we can find out the corresponding areas and other details, okay. Like say area we can find out, say total area will become 2 into individual area is 1137 for this section ISA 90 by 60 by 8, okay. So, this is coming 2274 millimeter square. Now, R minimum of the individual section is given 16.9 mm, right, and the effective length that will become as per the Coral provision as equal to the length between the intersections, that is 2.5 meter, that means 2500 millimeter, okay. So, the lambda max will become L by R minimum, okay. So, that we will get 2500 by 16.9, which is coming 148, and this is less than 350. So, we can say okay, right. So, from the slenderness point of view it is okay. Now, we have to find out the strength. So, for lambda is equal to 148 and assuming Fy is equal to 250 MPa, we can find out the sigma AC value from table 5.1. We can find out sigma AC, that will be becoming 45, which is at 150 plus 51 minus 45, sorry, this is at 140 and this is at 150, sorry, this is 150, this is 140, okay, by 150 minus 140 into 150 minus 148, right. So, from the interpolation we can find out the value as 46.2 MPa. So, sigma AC value for lambda is equal to 148 we are getting as 46.2 MPa, right. So, now we can find out the allowable working compressive stress, that will be 0.8 times of sigma AC. So, 0.8 into 46.2, right. This will become 0.8 into 46.2 will become 36.96 MPa, right. So, this is the allowable working compressive stress. Now, so safe load can be find out. Safe load will become area into the allowable working compressive stress. Allowable working compressive stress is 36.96 and area is 2274 and I am making kilonewton. So, I am dividing 1000, which is coming 84 kilonewton, right, which is less than the applied load. What is applied load? Applied load was 120 kilonewton. So, what we have seen? The assumed compressive stress was not okay, and for what we are getting the safe load which is less than the applied load, right. Now, let me see once again that here we are getting that required cross sectional area is 1714, right, and we are providing 2274 means 2274 we are providing and 1714 is requirement. So, we are providing more, still it is not safe, that is because we have considered the allowable compressive stress little high. Now, we have to change it, right. So, as the design is not satisfactory, so we can increase the section. So, let us try with say 2 ISA say 100 by 75 by 8. Okay. So, now the area will be from the structural handbook we can find out area, that will be 1336 into 2, which will become 2672 and R minimum will be 21.8 millimeter, right. So, lambda we can find out L by R minimum, that is L is 2500, R minimum is 21.8. So, this is becoming 114.7, which is less than 350. So, from slenderness point of view this is okay. Now, with this we can find out the sigma AC value. Sigma AC value will be from table 5.1 we can find out as this 64 plus 72 minus 64 by 10 into 120 minus 114.8, right. So, after calculating we will get 68.16 MPa. So, the allowable compressive stress for this particular section we are going to get as 68.16 MPa. So, allowable working compressive stress will be 0.8 times of that. So, 0.8 times of 68.16, this is becoming 54.53 MPa, right. So, safe load will be going to get safe load as 54.53 into area. Area of the combined section is 2672 and now I am making into kilonewton. So, this is becoming 145.7 kilonewton, which is greater than 120 kilonewton, right. So, design is safe, we can say design is safe. So, we have the applied load was 120 kilonewton and the section can carry 145.7 kilonewton. So, in this way it is safe. So, this is how we can find out the cross sectional property, means the section, the required section we can find out from this way. So, finally, what we can say, that provide 2 ISA 100 by 75 by 8 angle. For case A we can provide 2 ISA 100 by 75 by 8 angle. Now, let us come to the second case. In second case, what is there? That angles placed on opposite side. Of gusset plate. So, what we will do now? So, for this case, let us try with the earlier section, say 2 ISA 90 by 60 by 8. Let us try with this. Let us see first. So, area is becoming 2 into 1137, which is 2274 millimeter square, and R minimum is for this case 16.9, right, and L for this arrangement where the angles are placed opposite side of the gusset plate, L will become, the effective length will become as per Codal provision 0.85 L. So, this will become 0.85 into 2500. So, this is coming 2125 millimeter. So, the effective length is becoming this. Thus, the lambda will become L by R, that means 2125 by 16.9. This is coming 125.7, which is less than 350. So, we can say okay, right. Now, from table 5.1, for lambda is equal to 125.7 and Fy is equal to 250, we can find out the allowable compressive stress sigma AC, that will become as per table 57 plus 64 minus 57 by 10 into 130 minus 125.7. So, from this I can find out this as 60.01 MPa, right. So, safe load will be, this will become 60.01 into 2274 by 1000 for kilonewton. So, this is coming 136.5 kilonewton, which is greater than 120 kilonewton. That means the design is safe, right. So, what we have seen, that when the angles are placed opposite side of the gusset plate, the strength is increasing, strength of the built up section is going to increase, because if they are placed opposite to the gusset plate, then the effective length is going to increase by 0.85 times of the total length. That is why the effective length decreases, means the buckling effect will be less, that means the slenderness ratio will be less, that means the allowable compressive stress of the section will be more. If allowable compressive stress of the section becomes more, then definitely the strength will be more. So, with lower section we can provide. So, what we have seen, to carry 120 kilonewton load, if we choose the second case with a lower section, the design will be safe, whereas if we choose the case A, that first case, then we have to go for higher section, because in that case we see that the length is, means effective length is equal to the clear distance between two points. So, effective length is not going to reduce, that means the slenderness ratio is not going to reduce, that means the stress is going to decrease, allowable stress is less. As a result, the sectional properties has to be more, that means dimension has to be more, cross sectional area has to be more to carry that much load. So, we can provide 2 ISA 90 by 60 by 8. So, this we can provide. So, what we are seeing, that if the angles are placed in case of first case in this way, say this is the thing, then this will become 100, this is 100 and this is 75 and this is the gusset plate, right. So, this is ISA 100 by 75 by 8, this is 8 mm, okay. This is 16 mm gusset plate. So, case A. And in second case, what we have seen, that the angles are placed opposite to the opposite sides of the gusset plate, right. So, if we place like this, okay. So, this is 16 mm thick gusset plate, this is 8 mm and this is basically 60 mm, this is 90 mm, the section is ISA 90 by 60 by 8, case B. So, for case B we can use 90 by 60 by 8 to angle of 90 by 60 by 8 to carry 120 kilonewton load, whereas for this arrangement we need ISA 100 by 75 by 8 to carry the same amount of load. So, this is the way how we have to design a compression member with using built up sections. That the built up sections how to design, we have gone through one example from which we can understand. Now, this is not the end of the design of a built up sections, because so far whatever we have done is that the design of the main members of the built up sections. Now, as we told that built up sections, that means the sections consisting of more than one has to be tied in such way that the whole sections working means acting as a group. All the components are working means are acting as a whole. So, that is why we need to tie the members, the individual components. So, those tying can be done through lacing or battening, which will be discussed now shortly. Means as we do not have much time, so just I will give today some overview of the lacing and battening system, and next day I will discuss more about this, right. So, that means suppose there is two I sections, right. So, I sections are there and here it is made. Now, if we see the elevation, of this section, we will see like this, right. So, this is one I section, this is another I section. Now, it has to be tied in such a way, maybe this is called generally lacing system. So, it is tying in such a way that the whole systems are working together, right. That is why we call this as a lacing, this member is called as a lacing. So, lacing is generally preferred in case of eccentric loads. Flat bars are generally used for lacings. This is the lacing, and battening is normally used for axially loaded column, where the components are not far apart. Plates are used for battens. So, in case of battening, what we will see, if it is something like this, say two I sections are provided, then we will see that battening is done like this, right. So, here one battening, like this it will go on. So, this is the batten, some plates we are providing here, right. So, we can see that lacings are most commonly used lateral system. Lacings are most commonly used lateral system in built up compression members. Apart from flat bars, other common sections used are angles, channels and tubular sections. So, for lacing generally we use flat bars, other than that we use also channels, tubular section or angle sections. Now, lacing can be divided into two types. one is called single lacing, another is called double lacing. What is single lacing? Let us see. Single lacing, if we see, say 2 I section is there, right. Suppose these are the 2 I sections. Now the lacing is provided here. So if we see the elevation, this is 1 I section, this is another I section, right. So what we will do that this is how lacings are placed. This is called single lacing. This is the lacing. And in case of double lacing, what will happen? Suppose this is 1 I section, another 1 I section is here, right. So this is 1 I section, this is another I section, and these are laced in this way. So here we will see, so suppose it is going on like this in one way, right. So we can see so this is one, right, and another one will come similar way from this side, say like this, just crossing each other, right. So this is another lacing system which is called double lacing. Now whether we will go for single lacing or double lacing, it depends on the type of problem, how much load is coming, what are the type of load is coming, whether it is eccentric load, horizontal load is there or not. So all these things we have to see, and what are the sections we are going to take. Basically design engineers can, means from their experience, can choose whether it should be double, means whether we should go for double lacing system or single lacing system, right. So this is the way of lacing system. So now because of shortage of time, I like to finish our lecture today here, and the unfinished things means the starting things whatever we have started now, that is the lacing we will discuss in next class. So in today's lecture what we have seen, that how to design a compression member with built up section using built up section, basically that we have focused here. And for design of built up sections, we need to design also the lacing system which is tying the individual members to make them act together, right. So in next class we will discuss in details about lacing. Now today with this I like to conclude here. Thank you very much.